Welcome, everyone. My name's Jethro, and I'm here with my colleague, Ed. I'm the head of data science and engineering at Thames Water, and Ed is our digital twin lead. And we're going to talk to you today about how we are using digital twins to solve some of our trickiest asset problems in what is the largest water and wastewater company in the UK, Thames Water. To start off with, I'm going to assume many of you don't know who we are and don't know where we are. So I'll start with a few key facts about the company. So this is the area we serve. So we cover London and parts of the southeast in the UK. And these are our regional boundaries. Today we're speaking to you from a little town called Reading. This is where our HQ is based, just outside of London. And our company is named after the River Thames, which flows through London. We are a large utilities and asset firm in the UK. We serve about 15 million customers, and we've got a lot of different types of assets, network assets and so on. I won't go through all of the stats that are on this slide. You can read those at your leisure, but some key points are we are regulated by Ofwat as a regulated business, and we've got a lot of network assets. It's a very important point when we're talking about digital twins. And a few years ago, we had some problems with some of our performance commitments. So we have to achieve targets as a regulated business, and we were missing those over a period of a few years. And this motivated to invest in our data platform, and in particular, digital twin and graph technology. So for example, back in 2016, we had 8 major bursts, which caused a lot of customer disruption. Damage to property. In 2017, we then missed our leakage targets. Every year we need to reduce leakage coming out of our networks. And in 2018, we then had an event called the Beast from the East, which was a cold weather snap, which occurred over 24 hours. We had a huge temperature swing from -6 degrees almost C up to 7.5 degrees C in a space of a few hours, which caused all manner of problems in our water networks, which are very sensitive to temperature swings like that. So we were asking ourselves at this time, how can we better predict failure? How can we operate differently to how we're operating today? Why do pipes leak as they do? Can we detect that leakage in a more smart manner? And can we prioritize the work, our repair work, in a better way? Can we forecast demand in real time? So we've got a whole load of questions which are coming from these issues that were occurring over these years. And so we decided to invest in a new data platform and graph technology. And I'm going to hand over to my colleague, Ed, who's going to introduce the Thames Water Digital Twin.
Thanks, Jethro. So digital twins is somewhat a buzzword in the industry. While it has a good definition, it has a somewhat vague meaning. So the definition, a digital twin is a digital representation that serves as a counterpart to physical objects or processes. We've probably all heard that phrase quite a few times, but the value behind the digital twin is what you do with it rather than just what it is. So at Thames Water, we're developing what we call an ecosystem of digital twins. In line with the information management framework and the Gemini principles, instead of just developing a single twin, we're developing twins based on use cases or asset bases. And the reason why we've chosen this approach is that, as Jethro mentioned, we have over 30,000 kilometers of clean water pipes and over 100,000 kilometers of wastewater pipes. They have quite a lot of commonality between them. For example, they're both pipes buried underground, and they share connectivity with each other, but they have different problems which they're dealing with. They have different uses and different use cases. And so by developing it as an ecosystem, both of these twins can develop independently, can build to solve the exact problems which they've got at the moment without being limited by what's happening in the rest of the network. But they can also develop benefits based on what each of the other twins is developing. And so the water network can connect directly to the waste network. We're also exploring other twins, not just based on our networks. The first one of which is based on our hundreds of treatment works that we have. And those are not just driven by the connectivity of the assets, but quite a lot of their value is driven by the physical processes that are happening based on engineering models that have been used in the industry for many years. I'm also starting to look at our customer journeys, trying to make sure that we can map the experiences which our customers have through their time communicating with Thames. And so where does graph fit into all of this? We've talked quite a lot about the twins, and as you may have gathered from the last slide, what's underpinning those twins is the graph network. We have on the left-hand side a picture of some of the assets which we have, those being buried underneath the ground, so difficult to see, but here is an example of when they were first laid. And those can easily be represented as edges of a graph. And then we also have a number of point assets, whether those be sensors, pumps, valves, the physical locations where those assets are, and those can be represented as nodes. As we can see from the right-hand side, this is an example about how COVID transmission happened through a population, but we can use the same principles, use the same techniques to see how the water flows through the network or the sewage flows through the network. And it becomes immediately more tangible to people when you see that being visualized, rather than trying to just look at a relational database. And so with that, I'll hand back to Jethro to talk us through the first use case of the twin.
Thank you, Ed. So when planning this talk, Ed and I thought the best thing and the most useful thing for the audience of this conference is to talk through some real life use cases to give you a flavor of the kinds of things that we are doing at Thames Water with graph technology, give you a flavor of some of the benefits that we're getting from using this technology. And I've got a great team working on some very, very interesting problems. So it's really nice to be able to give you and have the opportunity to give you a bit of insight into what we're doing here. And hopefully, actually, it'll give you some ideas that you can take away and apply into your own company as well. So use case number one, we'll start with leak detection on water networks. As we discussed, we had a bunch of issues a few years ago with missing performance commitments. We don't want that to happen again. So we are deploying graph technology to help us meet our leakage targets. We know water leaks occur on our network. Sometimes it's not always obvious. You might be picturing leaks running down the road or down the pavement, but most leaks are actually underground. And across Europe, the average loss from networks is about 23%. So 23% of everything produced is lost through leakage. And the UK is around about that average, maybe slightly better. So very similar rates across the EU. Traditionally, to reduce leakage, you've got to find those leaks and then you've got to go and repair them. To find leaks that are underground, it's quite a challenge, and often you will use sound. So you can hear leaks, you can hear the hiss of leaks, and actually you would use something like a listening stick. So we've got an example of one of our technicians using a listening stick. It's literally a metal rod with a cup on the end, and you hold it down to the pipe and you listen to the sound of a leak. You can actually tell, when you're an experienced technician, you can tell the size of a leak based on the different characteristics of the sound. And with that, you can then prioritize the repair that gets done. Obviously, you can't have technicians listening to the network 24/7 across all of it. So what we tend to do now is use acoustic emissions sensors. These are magnetic sensors, of which you can see a few examples on the slide here, which clip onto our network very easily, and you can walk away and then you've got a permanent ear listening for leaks on our network. So we've got some motivation to solve leakage. We need to do that. We've got some new technology, some sensors, which we're deploying out on the network in their thousands. We've got about 25,000 or so of these acoustic emissions sensors dotted around our network. And we've got a few questions that we want to answer. So how do we optimally place these sensors? There's lots of them out there already. How do we view what we have and move them around so we can optimally find leaks? And using these sensors, can we localize leaks better than we are able to today? So can we use some graph technology to find a much smaller search area for our technicians to go and mark these leaks up on the ground with their spray paint? There's some challenges that we faced as a team in that leak sound only travels so far, and that's actually dependent on attributes of the network itself. So pipe material, for example, is very important. If you've got an old cast iron pipe, the sound travels quite a long way versus maybe a slightly newer ceramic pipe doesn't travel so far, and plastic pipes, obviously the new ones, it doesn't travel that far at all. So your range varies between maybe 10, 20 meters up to 120 meters or so, depending on pipe materials and some of the attributes. Things like junctions and stuff affect this, and bends as well. So quite a complicated set of kind of constraints on this problem. But the basic intuition here is shown on the slide. You've got an acoustic logger on the left there. You've got a section of pipe. Over the years, we'll have cut into that pipe and replaced it with new materials as we found and repaired leaks over hundreds of years. And so you don't often get a long straight of a single type of pipe. And on the right-hand side, you've got an actual leak itself, and sound will travel from the leak to the logger. That's the aim, anyway. And so using graph technology, we can determine the composite listening distance depending on all those different types of pipe in between the leak and the logger to understand our coverage. So this is what that looks like. This is an area of our network. It's actually is quite a large area in terms of their kind of water mains, so some of the larger pipes which connect between kind of housing areas. And you can see different colors on this chart, which represent the number of loggers which can hear that pipe. So you have some pipes with no color at all, they're just black lines, and no logger can hear that pipe. So if there's a leak on that section, we wouldn't be able to hear that leak using these loggers. Whereas in the middle of that map, we've got some lighter colored areas, greens, yellows, reds even, which represent a section of pipe where we've got 8, 10, 14 loggers potentially hearing that same section of pipe, which then leads to the question, actually, maybe we can start to optimize where we place these to reduce the amount of pipes that we can't hear and get a greater coverage. So in this area, for example, we had 88% coverage using 195 sensors. So the outcome of this is really good. We can optimize placement. We can use this this graph search technology to do that. We can help technicians localize the search area. So we can actually deploy this algorithm now to our technicians. We've got some web or mobile enabled apps, which they go and use to help them detect leakage. And actually an additional benefit of this is now we can go back through our history of data in our data platform, and we can link all our previous leaks and repairs with hundreds of thousands of historical sound files that we've had coming in from these sensors over the years, and create a really nice training data set, which we can then use for machine learning problems in future. So here you can see the outcomes. We can do each of those 3 things using graph networks. We wouldn't have been able to do that without graph technology. For use case number 2, I'm going to hand back over to Ed.
Thanks, Jethro. So we learned about how we are working on the leakage problem. Now we're going to look at how we look at the burst localization. So rather than these small leaks that occur on the network, these are when we would potentially describe as a catastrophic failure, where you have a huge failure of the main, and that causes a lot of water to leak out over a short period of time. And these can affect customers in a few different ways. The first bit is that you can cause a slightly lower pressure. So if it's one of these smaller types of bursts, then it will leak a lot of water, but there'll still be enough water being produced and pumped through the pipe network that it will still reach customers' houses, but it will be at a slightly lower pressure. But if the burst is slightly larger, or if it's taken too long for us to find it, it can get to the point where there's no water left in the pipe. It's all going out via this failure, this burst, and so there's no water available at people's taps. And if these bursts are really large, then they can cause flooding and property damage. The water can collect in the road, it can overwhelm the sewage system, and it can cause flooding in people's basements. And so this can cause quite a big problem for both our customers, but also Thames Water as well. And so the problem that we came with is that on the right-hand side, you can see the area which was isolated, where we knew that there was a burst happening within. So that's quite a large area, and that's because that's an area which we have real confidence in the data. We know what's happening in that area. And so when we send people out, we say, we know that there's a burst in this area, you need to go find it. And while that's good, if it's a smaller area, if it's a large area like that, it can take so long to find the leak that it would be better to use potentially slightly less use data we have slightly less confidence in, to start with areas where we think there's more likely to be a leak, and then go to the other areas once we've searched that area. And so that's the question. Can we use the existing sensors and use the knowledge that we have of the graph to help localize this burst to a smaller area with still a high degree of confidence so that we can locate the leaks faster? And so for this one, we use quite a lot of knowledge that we've got from our engineering colleagues in the business. And so when we talked to them, they were saying that when a burst occurs, you can see before the burst, the water's flowing straight through the pipe. Everything's flowing from left to right in this image. But then after the burst occurred, which was in the middle of this section of pipe, where the orange meter is, the flow has reversed. The flow's gone in the other direction. And so all the water is going towards that burst and is flowing out of it. And so by using the graph network and using this intuition that we've got from the engineering side of the business, we were able to develop an algorithm that was able to help us have a higher confidence in where the burst was within this area. The problem with this is, although we've got a really simple intuition on the right-hand side, our network is quite sparse and has a very high level of branching. When there's 2 meters and one section of pipe between it, it's quite easy to say the burst in there. But when we have 5, 8, or even 10 meters over a single section of pipe, working out the change in direction of these meters can be and can cause quite a high level of uncertainty, which means that we then can't be confident in the area which we've located the burst to. And so we wrote the first algorithm using the graph and using this reversal of meter flows, and it gave us a quite reduced section of pipe to go search for in this event. But there's a couple of things that stood out to us. The first bit is that we've got 2 different disjointed areas. That section on the right-hand side is a very small section of pipe, and so it could be quite quick to send someone out and search for it. But by understanding what was happening, understanding why the algorithm picked that area of pipe, we were able to work out that it wasn't behaving as we would expect. And so we're able to refine the problem and end up with a much smaller area of network, which we have quite a high confidence that it's in that area. But we can go down into the less and less confidence areas as the need arises, as we've proven that there's no burst in this section of the pipe. And so the outcome of this is that we have that much smaller area which people can search for to go find the burst. And that reduces the time needed to find the failure. And so the impact to the customers is much reduced. So for this final use case, we've been developing a proof of concept for automating our supply zones. What this means for us is that when some sort of water quality event occurs, we need to be able to locate the customers which may be impacted, locate the sections of pipe that may be impacted. And this allows us to make sure that there's no contaminants, no undesired foreign particles in our water network, which may impact our customers' health or their ability to have clean drinking water. And so we have a very dense network of pipes. There's lots of looping, there's lots of branching, and there's lots of sensors across it. And so in order to give us the most information we can about an area and to allow us to respond to these water quality events, we use a number of our assets and our assets like valves and meters to isolate sections of the pipe. And this means that when something occurs, we can either shut a valve to isolate where these foreign particles have been introduced, or we could open a valve, and that means that the area which is contaminated can get fresh water from somewhere else. And so what we need to do is we need to create an algorithm that identifies when these changes occurred, what is the new state of the network, what are the new water supply zones that there are. As it is, it's currently a manual process. And so there's people looking over the network maps that we have, doing network traces to work out which areas are being fed from where. And that's quite costly. And it was also difficult to do in the event that something occurs. If you know that something's in the network, you want to respond immediately. And if there's an algorithm that's already computed what is the state of the water supply zones, rather than having to go to someone that's experienced in it, then we can respond much more quickly to these events. And so the question is, can we use these graph techniques to automatically update the water supply zones instead of the manual processes? And so the approach that we took was a combination of the domain expertise. We worked with these people that had experience updating these water supply zones, learned what they could, learned what we could from them, and tried to abstract their knowledge into an algorithm. And it might not be 100% correct, but it would give us the best solution that we could in the short notice that there is. And we did this by using a random walk algorithm. So this agent walked down the graph network, looked at the current state, looked at the status of the valves, looked at where else it had walked in the area, and allowed us to create a heat map of where certain water is flowing within our network. And by using that domain expertise, we're able to apply all sorts of constraints to the network, so that the agent would respond as the water would do in the network. So although we've got this agent working, it's currently in the proof of concept stage. We're able to show our stakeholders, show the senior managers what we're capable of doing, and generate investment for this program of work. And we're able to generate more value from the graph by applying these sorts of algorithms. Although we've used it for the water supply zones, there's many other use cases within Thames, which we can use similar agents walking through the network to provide value to it. We're also able to embed more domain knowledge and features into the graph that exists, and take those learnings to the other twins that we have. The waste twin, we could use a similar agent given it's built on the same architecture. And then we can move towards a production-ready system to automatically locate these water supply zones.
Okay, thank you, Ed. So hopefully that has given you a flavour of the kind of techniques and algorithms and experimentation that we're using Graph for within Thames Water. I hope that's been helpful. I hope that's been enlightening. And we will be around for questions during the Q&A at the end. Thank you.